Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating paper on transparent reasoning models using sparse autoencoders, or SAEs, and it's got some interesting potential for bridging the gap between AI and neuroscience.
Yeah, this Resa paper, I think it's a step in the right direction, especially when you think about the current push for more explainable AI. For a long time, we have treated neural networks like black boxes, but with transparent approaches, we can get one step closer to AGI.
I'm not entirely convinced. While transparency in AI is definitely a worthy goal, I'm skeptical that just tweaking deep learning architectures like SAEs is really the answer. It still feels like we're fundamentally missing something about how true intelligence works. I think neuro-symbolic approaches might be better.
I'm with you somewhat, Sarah. While I appreciate the effort to make AI more transparent, I worry that we're still using a brute force approach. I have this hunch that the real key lies in algorithms that can understand and translate between different spatiotemporal coordinate systems. Current deep learning just doesn't seem to grasp that.
Okay, so let's break down this Resa paper a little bit. The core idea is to use sparse autoencoders to build models that are more interpretable. Essentially, the sparsity constraint forces the network to learn more compact and meaningful representations of the data. Instead of dense activations across all neurons, only a few are active, supposedly making it easier to trace the reasoning process.
Right? And that's where the transparent reasoning part comes in. Because you've got these sparse activations, you can theoretically follow the chain of activations that leads to a particular decision. It's like you can see which neurons are thinking and how they're connected to the final output. With increasing volumes of available data, we should see more advances in this area.
But is it really reasoning? Or is it just a more interpretable form of pattern recognition? I mean, these models are still trained on massive datasets, and they're still essentially learning statistical associations. Where's the actual understanding? Where's the ability to generalize to situations they haven't seen before? I don't believe we are understanding the why behind these complex neural networks. What are the mathematical relationships in deep learning outputs? That is what we should be looking into.
Exactly. That's my concern too. Imagine you're trying to teach a robot to navigate a room. A deep learning model might learn to recognize obstacles and avoid them. But does it understand the concept of obstacle? Does it understand the spatial relationships between objects? Can it reason about how to plan a path around a novel arrangement of obstacles? Probably not. The model is simply learning what worked in the training data. We need for our current systems to understand relativistic distortion of space.
Well, I think you're underestimating the potential here. Yes, current deep learning has limitations. But the Resa approach, by forcing sparsity and transparency, is moving us towards a system that can, in a sense, explain its decisions. And as we get better at training these models, and as we generate more and better data sets, that explainability will translate into true understanding. The availability of data is crucial, and combined with approaches like Resa, we can potentially mitigate biases and make the models more robust.
I think there's something to be said for the neuroscientific implications as well. If we can link the activations in these SAE models to actual brain activity, we might gain some insights into how the brain itself performs reasoning. I'm thinking about Resa's transparency approach. If we can link the model's outputs to measurable brain activity where it might help us understand the fundamental aspects of human cognition.
Okay, I'll grant you that. The potential for neuroscientific validation is interesting, but I still think we're going about it the wrong way. Instead of trying to reverse engineer the brain using deep learning, why not start with a solid foundation of symbolic reasoning and then use neuroscience to inform how we implement those symbolic systems? That way, we have a framework for representing knowledge explicitly, which is what I think is currently missing. More nuanced mathematical frameworks may allow analysis of structure and temporal aspects of information processing.
I agree with Sarah on that. We need to start with principles, not just data. Take the concept of time, for instance. Current AI treats time as just another feature in the data. But time is fundamentally linked to space. A truly intelligent system needs to understand how time changes depending on your frame of reference, how it is related to the speed of light. How do we design algorithms that inherently understand and manipulate different coordinate systems and different frames of reference? I want to see AI that understands time dilation or the relativistic distortion of space.
But wouldn't it be possible to eventually learn those relationships through data? I mean, if you feed a neural network enough data about relativistic physics, couldn't it eventually learn to model those effects? The models are getting better all the time, and they're learning these abstract relationships using mathematical outputs from deep learning.
That's the big question, isn't it? Can you get true understanding just by scaling up deep learning, or do you need something more fundamental? What about Resa's approach to transparent reasoning? How does that compare to neuro-symbolic models? Are there potential overlaps or synergies? Could the transparent reasoning mechanisms in Resa be adapted to handle more symbolic representations, or can symbolic reasoning be integrated into an SAE architecture?
I think the latter approach is more promising. Integrate symbolic reasoning into an SAE architecture or something similar. That way, you can leverage the strengths of both approaches. You can use neural networks to learn low-level features from the data, but then you can use symbolic reasoning to build higher-level abstractions and make inferences. We're chasing correlation over causation.
Exactly. Think about how humans learn. We don't just memorize data. We build mental models of the world, and those models are based on principles and relationships. They are models that can translate between frames of reference. We need to find a way to encode those principles into AI algorithms, and that might involve completely different mathematical frameworks than what we're currently using.
So you're suggesting we abandon deep learning altogether? That seems a bit extreme, especially given its successes in areas like image recognition and natural language processing. Why abandon a fruitful path of research? I still think deep learning and more data is the path to AGI.
No, not abandon it entirely. But we need to recognize its limitations. Deep learning is good at pattern recognition, but it's not good at reasoning. And reasoning is essential for true intelligence. We need to be focused on how to create truly intelligent algorithms and not get lost in the sheer scale of the datasets.
I think a hybrid approach makes the most sense. Leverage the strengths of both deep learning and symbolic AI. And I think the key is to find ways to make these systems more transparent and interpretable, so we can actually understand how they're working. The potential for creating truly intelligent machines that can learn and adapt like humans is incredibly exciting. However, understanding the underlying mechanisms of biological intelligence is paramount before replicating it flawlessly. This requires a more collaborative approach between neuroscientists and AI researchers.
Okay, I can see the value in that. A hybrid approach. Use deep learning to learn features, and then use symbolic reasoning to build on top of those features. It is a structured approach.
But even within that hybrid approach, we need to be thinking about how to represent space and time in a more fundamental way. How do we encode the principles of physics into these algorithms? How do we allow them to reason about different frames of reference? If we can crack that nut, I think we'll be much closer to AGI.
Agreed. And I think that also means focusing on more efficient learning algorithms. The current emphasis on massive datasets and deep learning feels like a brute force approach. Perhaps there are more nuanced, biologically inspired computational approaches that can lead to more efficient and meaningful intelligence without requiring such enormous resources.
So where do we go from here? What are the key research directions that emerge from this discussion?
From my perspective, it's all about scaling up these transparent deep learning models and finding ways to train them on even larger and more diverse datasets. I want to see how far we can push the boundaries of what's possible with data-driven AI.
I think we need to focus on developing new neuro-symbolic architectures that can explicitly represent knowledge and reason about the world. And we need to ground those architectures in neuroscience, so we can ensure that they're actually capturing something meaningful about how the brain works.
I'd like to see research into algorithms that can understand and translate between different spatiotemporal coordinate systems. I think that's a fundamental piece of the puzzle that's currently missing. So, building algorithms that can translate between different coordinate systems is what I'd like to see.
And I think we need to focus on bridging the gap between AI and neuroscience. We need to find ways to validate these AI models with real brain data so we can actually understand how they're working. And that means developing new tools and techniques for analyzing brain activity and linking it to computational models. Also, the brain's ability to adapt and change its structure based on experience is fascinating and critical to intelligence. If we can integrate this principle of plasticity into AI models, we might achieve a more dynamic and evolving form of intelligence rather than a static system.
That's a good point. The neuroscientific validation is key. That will help us understand the why.
Yes, that's the direction that I would take.
Me too. Ground it in reality.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. Hopefully, this discussion has given you some food for thought about the future of AI and the quest for true intelligence. Until next time.